This lesson is Transformations. It ties in with SOLG 3, C, and D, investigating symmetry and determining whether a figure is symmetric with respect to a line or a point, and determining whether a figure has been translated, reflected, rotated, or dilated using coordinate methods. Several types of transformations. Reflections, these are like mirror images as seen across a line or a point. This figure on the left is reflected along where the mirror line would be down the middle, and it's reflected over to the right. It just flips over. Translations or slides. This moves the figure to a new location with no change to the looks of the figure. This figure translates upward. It doesn't turn around or flip or anything like that. It just does a slide. And rotations. This turns the figure clockwise or counterclockwise, but doesn't change the figure. So the arrow pointing to the right would rotate clockwise down and point this way. Reflections can be reflected using a line or a point. All measures are preserved, but in a mirror image. So the shape and the size stay the same. It's just reflected around. For example, this figure is reflected across line L. It starts on the left, and you could flip it right over line L to be facing to the right. Every point is the same distance away, reflected over to the right-hand side. When you are on the coordinate plane, if you reflect across the x-axis, the x value stays the same and the y value changes. What was above is now below. What was below is now above. That's why the y value changes. When you reflect across the y-axis, you're moving left or right, so the x value changes. What was left moves right, and what was right moves left. If you start with figure L, if it reflects across the y-axis, that means the x values change. The 0.21 becomes negative 21, and the 0.54 becomes negative 54. When you reflect across the x-axis, everything above is now below. 21 becomes 2 negative 1, 54 becomes 5 negative 4. Sometimes there's a specific line that you reflect across. A line y equals a, that's a horizontal line through that number. A line x equals a is a vertical line through that number. Just mark the corresponding points equidistant from the line. For example, if a point is 2 units above the line, then its corresponding image has to be 2 points below the line. In this example, we're going to reflect the figure across the line y equals 1. That's a horizontal line through 1. The point 2,3 is 2 units above, and it will reflect to 2 units below, to 2 negative 1. The point negative 3,6 is 1, 2, 3, 4, 5 units above the line. Reflect it 1, 2, 3, 4, 5 units below the line to negative 3, negative 4. The point negative 6, 2, it's 6 left, 2 up, but it's only 1 above the line. Move it 1 below the line. Everything that's on the top of the line goes the same distance below the line. Now let's talk about lines of symmetry. If a line can be drawn through a figure, so the one side of the figure is a reflection of the other side, then the line is called a line of symmetry. Some figures have one or more lines of symmetry. This figure has one line of symmetry. It can fold where the top would completely overlap the bottom. This has two lines of symmetry. Each one of these you could fold the figure and it would perfectly overlap. A square has four lines of symmetry. A circle has infinite lines of symmetry. You can fold it in half an infinite number of ways. This parallelogram doesn't have any lines of symmetry. There's no way that you could fold that perfectly in half. Some figures have point symmetry, and that's when every part has a matching part that is the same distance from the central point, but in the opposite direction. So for example, in this card, consider the center right here. The K is up and to the left. We'll go the opposite direction, down to the right, and there's another K. The sword is up to the right. The other sword is down to the left, going the opposite direction through that point. You could also look and say that this figure could rotate around and perfectly line up with itself again. It looks the same viewed from opposite directions if it's rotated around. This is sometimes called origin symmetry. Translations are also called slides because you don't turn it or flip it, you just slide the figure over. If it's simply moved to another location without change to its shape or direction, it's called a translation. If a point is moved a units to the right, then you'll add a to the x value. If it's moved b units up, then you'll add b to the y value. Remember, moving left or right changes the x value. Moving up or down changes the y value. If you're moving left, a units to the left subtracts a from the x value. If you move b units down, then you'll subtract b from the y value. For x, right is positive, left is negative. For y, up is positive, down is negative. In this example, image A translates to image B by moving right 3 and down 8. So each point moves right 3, down 8. This point, right 3, down 8. This point, right 3, down 8. So for each of those coordinates, we will add 3 to the x value since we're moving right, and we will subtract 8 from the y value since we're moving down. Point 25 moves 3 to the right, so we'll add 3, becoming a 5, and it moves 8 down, so we'll subtract 8 from the 5, and it becomes negative 3. For rotations, an image can be rotated about a fixed point. For example, the blades of a fan rotate about a fixed point. An image can also be rotated over two intersecting lines by using composite reflections. In this example, you have figure A, and you have two intersecting lines, M and N. If you take figure A and reflect it over line M, it moves down here to figure B. Then take figure B, reflect it in line N, and it reflects over to figure C. Go from start to finish. From A to C actually becomes a rotation. When you reflect things twice across intersecting lines, the result is a rotation. When you're on the coordinate plane, you can rotate an object around a fixed point, and that point is called the point of rotation. If you rotate counterclockwise 90 degrees about the origin, switch each coordinate, and then multiply the first coordinate by -1. So the point x comma y actually becomes -y comma x. Flip the coordinates and change the sign on the first one. So if we take this segment and we want to reflect it 90 degrees counterclockwise, the point 1, 2, flip it and change the sign on the first one, it becomes -2, 1. 6, 2, flip them and change the sign on the first one to -2, 6. When you redraw that, it goes right here. So the end result, it's like you took the original and rotated it that way 90 degrees, rotated it that way 90 degrees, counterclockwise about the origin. Another way to look at it is this point, it is 1 right, 2 up. Turn your head 90 degrees counterclockwise, so tip your head to the left. When you do that, look at the origin again, go 1 right, 2 up. There's your new point. Likewise, point 62 is 6 right, 2 up. Now turn your head 90 degrees counterclockwise from the origin, go 6 right, 2 up, and there's that point. Turn your head in the direction of the rotation and redraw based on your new orientation. Sometimes you rotate 180 degrees. That's a half circle around. When you do that, just change the sign on each coordinate. So 1, 2 becomes -1, -2. 6, 2 becomes -6, -2. Another way to look at it is point 1, 2 is 1 to the right, 2 up. If you rotate your head 180 degrees completely upside down from the origin, go 1 to the right, 2 up, and there's your new point. 6, 2 is 6 to the right, 2 up. Rotate your head all the way upside down from the origin, go 6 right, 2 up, and there you are again. Dilations occur which changes the size of a figure, but not its shape. A dilation can either get larger or smaller, and it's a similarity transformation. The shape doesn't change, but the size does. Since a dilation changes figures proportionately, it has a scale factor k. If the absolute value of k is greater than 1, then the dilation is an enlargement and the figure gets bigger. If the absolute value of k is between 0 and 1, the dilation is a reduction and it gets smaller. And if the absolute value of k equals 0, then the dilation is a congruence transformation, so the size doesn't change at all. In this figure, the center is C, and we'll start with segment AB. We will dilate it to segment EF. The distance from C to A, we'll call that 1 unit. And then the distance from C to E, if that's 1, that much is 2, that much is 3. So E is 3 times the distance away. The same thing works with B and F. From C to B, that counts as 1. Go the same distance again, and the same distance again. And F is 3 times the distance away from B. That means the scale factor is 3, since the distance to the new segment is 3 times the distance away from the old segment. Also, that means that the length of segment EF is 3 times as long as the length of segment AB. The distance is 3 times away, and the length is 3 times. In this figure, we start with segment AB, and then the distance from C to A is 1. Then it backs up. R is only half of the length away. So from C to A, if that's 1, R backs up to the halfway mark. From C to B, that counts as 1. C to W is also at the halfway mark, which means that the scale factor here is 1/2, which means that segment RW is only half as far away as segment AB was from C, and the length of segment RW is only half the size of the length of segment AB. In a dilation, you not only are the distance away from C, the scale factor's value, you're also that length. So segment RW, half the distance away from C, and segment RW is half as long as segment AB. Finally, sometimes you want to know measures of segments that are dilated. If you take your original segment AB, it's 6 units long. Then dilate it with a scale factor of -4. Since the scale factor is -4, the absolute value of that is greater than 1. The absolute value is 4, which means that the new segment is 4 times 6, which is 24 units long. Take it, the scale factor times the original length. If the scale factor is 2/3, 2/3 is between 0 and 1, so it gets smaller. 2/3 times 6 is 4. So 6 got smaller, and now it's 4 units long. If the scale factor is 1, it's a congruence transformation, and the image is still 6 units long. Correct this 1 to a 6. And that does it. So whatever the transformation is, move the figure according to the directions, and you will end up with the new image.